Every day, 200 children lost their lives to pneumonia. In 2019, pneumonia killed more children than any other infection disease. Till now, PCV injection is done to prevent pneumonia. However, it causes pain and trauma for children and have risks for disease transmission. Therefore, the innovation of microneedle patches is a vaccine delivery solution for children because it minimizes pain, works faster, effective, has high reproducibility, and bioavailability. However, the challenge in distributing microneedle PCV13 is maintaining its storage with temperature of 2 to 8 degrees Celsius. Therefore, let us introduce ourselves. I'm Nabila Dini Aulia and Raisa, and our innovation is pneumococcal conjugated vaccine microneedle patch with self-repellent from Bombyx Mali and aerosol silica from Number Lapindo for prolonged shelf-life in vaccine supply chain. In this research, improvement of PCV microneedle patch shelf-life can be achieved by adding self-repellent and silica aerogel. Self-repellent is proven by Olivia Hallisey at 2016 to add shelf-life to ELISA kit in room temperature up to 7 days and later modified with addition of nanosilica up to 28 days. On the other hand, aerosol silica has the potential to be implemented in biomedical field, particularly drug delivery due to its unique physical, chemical, and mechanical properties. Silica can be obtained from Lapindo Mat in Sidoarjo, which separately contains up to 53.08%. A combination of both material is designed as a coating for microneedle patch, in hope of increasing efficiency in PCV vaccine supply chain to prevent pneumonia in children, anytime and anywhere. The purpose of this research is as follows, which are determining synthesis process and characterization of silica aerogel from Lapindo Mat, self-repellent from Bombyx Mali, and formation and evaluation of PCV13 microneedle patch coated with self-repellent and aerogel silica. This research is done from October 2024 until February 2025, located at Lapindo Mat site, Mantri Malang, Lab Riset Terpadu UB, Lab Bioscience UB, Lab Sentral UMM. Next is research methods, which are synthesis of aerogel silica, purification of self-repellent, and making PCV13 microneedle patch. Lapindo Mat is obtained from Siling Village, Porong District, then dried using oven and then calcined. Then the sample is cooled and sieved. Silica synthesis is done using 3 molar sodium hydroxide solution. Then the filtrate is separated using filter paper, then added with 1 molar hydrochloric acid until a white precipitated form. Then separated with filter paper and washed to obtain silica hydrogel. Then it is homogenized and put into a syringe tube and oven. Next is washing with methanol to become aquagel, then put into a mixture of methanol, TM6 hexane for surface modification and become silica gel. Then it is dried and then heated at ambient pressure to obtain silica aerogel. The purification of self-repellent from Bombyx Mali silkworms begin with cutting and cleaning the cocoons. Then the degumming process is carried out using sodium carbonate and washing with distilled water and drying. Then the dissolution process is carried out using Ajisawa solution. Furthermore, the silk fiber is purified with dialysis using cellulose membrane. The microneedle mold is designed using silicone rubber and then added with benzoyl peroxide catalyst. After drying, it's then removed from the microneedling cartridge. Then PVA% solution is poured to silicone mold, centrifuged and dried. The vaccine mixture is made by mixing the vaccine, trehalose albumin, DMSO, and 8% NaCMC. Then mix it with the dried PVA. The front microneedle patch is coated with self-repellent and silica aerogel mixture with variation of composition using dip coat method, leaving 1/4 of the tip uncovered as drug dissolved pad, creating the effect of hollow microneedle. The patch is then attached to a transparent waterproof plaster pad and then storing it in a package, avoiding direct light or moisture. For further evaluation, which are morphological analysis using SAM, penetration test using Franz diffusion test, and Barfoot test.
Silica extracted from Lapindo Mat was analyzed using SAM and EDS. Morphological analysis showed agglomeration affecting surface structure. EDS result indicated low silica content, which is 44.12% due to sodium chloride contamination from extraction and organic carbon content. Hence, purification involves heated aqueous washing to remove salt and high temperature calcination to eliminate carbon is done. This increased the silicon content up to 90.66%. Silica aerogel was synthesized using TMCS for surface modification, reducing shrinkage during drying by replacing the hydroxyl group in the silica pore with the trimethylsilyl group, converting it into oxyl trimethyl, forming hydrophobic white granules. Sulfibrin was purified by decoming Babix cocoons with sodium carbonate, reducing sericin content successfully. Dissolution in Ajisawa solution obtained from calcium chloride, methanol, and aqueous in 1 to 2 to 8 molar ratio formed a yellowish solution. Later, purified via cellulose membrane dialysis with content stir of 200 rpm for 4 days, yields SF concentrations as 0.4 gram per milliliter. SAM shows a fibrous network protecting microneedle from degradation. Microneedle mold is modeled after commercial microneedle cartridge and made using silicone rubber with diameter of 1.1 cm, height of 1 cm, and can hold 350 microliters of active ingredients. Microneedle mixture is poured into the mold, dried, and then evaluated using SAM. The obtained microneedle have conical shape with sharp apex with a length of 707.5 micrometer and a width of 160 micrometer, having great potential in piercing the skin with no pain. Coating with sulfibrin silica aerogel is made with variation of 1:1, 1:2, and 2:1 ratios. SFAS coating is carried out at the base of the needle up to 3/4 of the needle height, leaving the tip uncoated as a drug dissolution pathway, creating a hollow microneedle effect. This is obtained because SFAS as a coating is hydrophobic and indissolvable. SFAS mixture is stripped with a matured foam with a micropipette. With the method of deep coat, then microneedle are lifted and then dried. SAM showed fibrous SF morphology with dispersed silica aerogel, though some aggregation and surface roughness were observed. The stability and penetration efficiency of PCV13 microneedle patches with SFAS coatings were evaluated using the French diffusion test and Bradford test. Samples are uncoated microneedle patch as controls. SFAS combination with ratio 1:1, 1:2, 2:1 is done every week until the 21st days of storage. Microneedle patch coated with SFSA 2.1 shows highest penetration in all time points. Result shows that PCV contents decrease with the increase of temperature, indicating denaturation of protein. Despite that, SFSA 2:1 provide optimal vaccine protein across the temperature, and uncoated patch shows the lowest result, highlighting the significant improvement in stability after coating. Testing over 21 days demonstrate that SFSA 2.1 maintained the highest penetration values across all temperatures, likely due to its protective matrix. Even at 40 degrees Celsius, it retained higher penetration, indicating improved vaccine stability and shelf life. With this innovation, we hope vaccine distribution system can reach children far and wide with sustainable, painless, and effective system, so pneumonia won't take lives of more precious generation.